What if I told you that with a simple Google search, you could find a picture of what the universe looked like shortly after the Big Bang? As it turns out, the darkness between the stars of the night sky is actually filled with the faint glow of light left over from the formation of the universe as we know it. This light is known as the cosmic microwave background, or CMB. In 1964, two radio astronomers by the names of Arno Penzias and Robert Wilson decided to point their telescope at the sky and see what they could find in the black nothingness of space. Their telescope wasn't like a normal telescope that you would use to look at planets with your eyes. It was a radio telescope, which simply means that it collects light of a much longer wavelength, and thus a lower energy, and uses that light to create a picture. When they pointed their telescope at the sky, they were quite surprised by what they found. The telescope detected a very low but persistent level of noise, no matter which direction they pointed it. They tried everything to figure out what was causing this noise, and they thought they had solved it when they realized that a family of pigeons had set up a nest in the satellite dish of the telescope. However, even after cleaning out all the pigeon byproduct, the signal remained. Penzias and Wilson didn't realize it at the time, but they were the first people to measure the light that was left over from the Big Bang, which permeated throughout the whole universe. Let's take a trip back to roughly 380,000 years after the Big Bang. Even at this point, the universe was very hot. So hot, in fact, that the constituents of matter were moving too quickly to join together. Think about two magnets, held in such a way that they would normally attract one another. Now imagine trying to move them past each other so fast that they don't even touch. That's what was happening to the positively charged protons and negatively charged electrons at this point in the universe. They were zipping back and forth so fast that they couldn't even stick together to form a hydrogen atom, which is the simplest atom of any element. In addition to all of these charged particles zipping around at high speeds like a demolition derby, there was also a ton of light filling the whole universe, like a white-hot forge. Now, something you may not know about light is that it is really made up of electric and magnetic fields, so as the charged particles flew around the universe, they also interacted with the light everywhere they went. It was a crazy mess of particles and light, all crashing into each other and changing directions. But, at some point, things finally cooled down enough so that the electric attraction between the protons and electrons could overcome their speed, and they began to stick together to form hydrogen atoms. When this happens, the positive and negative charges of the protons and electrons cancel out, and you're left with atoms that have a net zero charge. So, they can't block the light from shining. At this very moment, when the particles in the universe formed atoms, it freed up enough space in the universe so that the light, which had been crashing around since the Big Bang, could finally flow freely. Since that point in time, the first atoms went on to form stars, which formed other elements and eventually our planet and us. However, that light, which was set free by the genesis of atoms, just kept shining, and it has been zipping around the universe ever since, filling all the gaps and spreading out to make sure that no point in the universe is ever truly dark. If this seems confusing, just think about a camera. When you take a picture, the light bounces off of whatever you are photographing until it finally flows freely into your camera lens. After that, it hits either a piece of film or a sensor and creates an image. That image is simply a 2D cross-section of that light flowing freely from whatever it bounced off of before. What Penzias and Wilson did by pointing their telescope into the sky was to finally look at the photograph of the Big Bang that had been developing for billions of years. To better illustrate this idea, you can actually conduct a rather simple demonstration at home. All you need is 2 plastic or paper cups, some black tape or duct tape, parchment paper, and something sharp and pointy. First, you just need to wrap the sides and bottoms of the cups with the tape to make sure that no light can bleed through the material. Next, take a small square of your parchment paper, just big enough to cover the top of the cup, and wrap it around the top like a lid. Secure the parchment with a long strip of tape and then tape the other cup down over the parchment, securing it with a piece of tape as well. Make sure all holes are sealed with tape around the joint of the two cups so that no light can get in. Now, take a cutting implement and cut a decent sized hole in one end, about 1/2 inch wide. This will be the eye hole. Using a push pin or something sharp and round, punch a tiny pinhole in the other end, as close to the center as possible. What you have just made is a makeshift camera. As light passes through the pinhole, it projects an image onto the piece of parchment between the cups. This parchment mimics the film or sensor inside your camera. Rather than saving the image, you simply use the other cup as a viewfinder and see the image through the paper. As a fun optics side lesson, you might notice that the image is upside down. Take some time to think about why that might be, and if you think you have the answer, throw it in the comments down below. Anyway, in addition to being a camera, you can also think of this demo as a small version of an evolving universe. The pinhole is the Big Bang, where everything is super dense and hot. Then, the universe expands, and the light bounces around until the point when atoms form, and it can flow freely without bouncing off anything. This is when it hits the paper and creates an image. From that point on, the image will remain, but it will simply expand to fill the space, slowly losing detail and brightness. If we made the second cup longer, the image on the paper would be the same, but it would be harder to make out the details of the image. For cosmologists today trying to study the CMB, it is like having one cup that is 380,000 light years long, and a second cup that is 13 billion years long. So, needless to say, the CMB is a very weak signal, and the details are very low resolution. But, with the right experimental tools, we can still make out the image of what the universe looked like at the time when the very first elements began to form. And this can give us clues as to the validity of our cosmological theories. Simply by looking into the sky and pointing a telescope at nothing, we were able to uncover a secret that the universe has been dying to tell us. So, the next time you find yourself counting the stars, take a second to consider the space between them and what it might be trying to show you. And I encourage you to try making your own universal camera at home. Thank you for taking this journey to the early universe with me, and if you like this discussion, feel free to comment down below what you would like to hear about next. And, as always, don't forget to season your food with your heart and to season your mind with science.